Hi everyone, welcome to this tutorial on agent-based modeling using the Mesa library in Python. So today we're going to build together a minimal agent-based model using the Mesa library in Python. And this model that we're going to build today uses Mesa version 3.0.3. However, if you have a newer version of Mesa, at the moment, the newest is 3.2.0. The model will still work with that version. However, it doesn't really utilize all the new features that the latest version offer. This is the outline of the tutorial of today. Learning objective, little about how to install Mesa. We are gonna make a recap on classes and object-oriented programming. We will cover all the aspects of an agent-based model using Mesa, setting up the model, adding agents and the step method, adding agent or model behavior. We will talk about the Mesa spaces. So those are the spaces where the agent would be located at, and moving also around. Moving agents, how agents actually move from cell to another cell. How do we collect data? How do we visualize data? How do we use a batch runner, which allows us to perform a lot of simulation runs very easily instead of us creating for loop to do that? And a little about accessing data with pandas. And finally, we're gonna wrap up this tutorial. Learning objectives. At the end of this tutorial, you should be able to explain what object-oriented programming is. So you should be able to tell what the difference between a class and an instance of class. You should know what inheritance is. Mesa relies a lot on classes for its implementation, so you should understand these concepts and how to use them. At the end of this tutorial, you should also be able to recall some of the main Python command. You should be able, and this is the most important point, you should be able to build a minimal agent-based model using the Mesa library while having access to online and external support, of course. You are not expected to memorize everything. Everything is out there in the Mesa documentation. You will be able to use it and you will have access to it. At the end of this lecture, you will not be able to create a complex Mesa model without facing challenges, even if you have access to external online resources. Because at the moment when you start implementing some complex ideas into an agent-based model, then you will face some complexity. But as you practice, you should be able to, develop the skills that you need to create complex ABMs. And of course, we will not be able to know all Python commands by heart. Nobody does, and that's not expected from me. So in this tutorial, we will not cover all aspect of Mesa and Python. Of course, it's your responsibility to acquire additional knowledge that you need. So bear that in mind, because we cannot really use all the function and the functionality that Mesa offer in this tutorial. There are many, but we're gonna use as much as possible in this tutorial just to get you started and to have the good foundation to carry on your own. Now, Mesa library has a lot of methods implemented there just for us to use in an ABM. So please consider going over the documentation of Mesa and just know what exists. Because if you know what exists, you will not, in a lot of, situation, you find yourself hard coding everything, right? But sometimes there are some functionality that are implemented for us. So if we know that these functionalities exist, so we could use them instead of coding them from scratch. Installing Mesa. For students who will be following the course, you will not have to install Mesa because you will be using a tool called Vocarion, where Mesa comes pre-installed for you. However, for those who would like to run this code on their local environment, you have to set up the Python environment first. And for that, I have prepared a guide on how to set a local environment on your own computer. and I left a link in the description below. Recap on classes. There are two things that you should be aware of. The first thing is a class, and the second thing is instance. And usually we say the instance is an instance of a class. What does that mean? You can think about class as a template, and you can think about instance as a filled copy of that template. So this is a template. Template is like an unfilled form. So you know what form, like a PDF form where you have some fields that you need to fill yourself. So this you can call class. So the unfilled form is a class where you have here, for example, name, age, height, and nationality, but there are no values. Okay, and in Python, we call these attribute of class. But because we don't have values, we still call that class. But now imagine that you would like to, to have a copy of that form that you fill yourself with your own data. Then you create a copy and you fill it with your own data. And we call that a filled form, or we call that an instance of the class. So a filled form of the unfilled form that's coming from the unfilled form, that's copy from it, and an instance of the class. This is a first instance, but we could make other copies, more copies. We could make another copy with different data. Now with different name, different age, different height, different nationality, and that is another instance. It's coming from the same place, from the class, the main class, but it has some differences in values, but also other differences that today we're gonna see. And also a third instance with different information, with different values here. So here we have three instances of a class. Of course, we can have an unlimited number of instances that are coming from the same class. Now, how Mesa uses classes to build a model. In Mesa, we have two main classes that you need to have too many classes to build a minimal model. The first one is called an agent class, and the second one is called a model class. Because at the end, we want to create a model that has agents inside. So these are two classes that we must have for any agent-based model to be called an agent-based model in Mesa, of course. So the agent, it's the model class first. Let me give you an example. Imagine that you want to create a model that's a country. For that model, you create a class first, a template, right? Now for this example, we create a class called country. And inside those brackets, we write model. Now this technically means that the class that we're creating is going to inherit from the model class that's defined inside Mesa. But this also in simple terms means the country class that we are defining is a model class, and it's not an agent class, but a model class. Now for this country, we need only one attribute, one variable. You can also call it attribute or variable, which is a country name. So if we are to create a country from the country class, then we will need to give it a name. So let's create a model of a country that doesn't have any agent inside. Let's see how it looks like. So if we want to build a model out of that single class, we're going to call country class, this one, and we need to pass its name. So we're gonna give it the name Netherlands. This means we will create a country and its name is going to be Netherlands. And this is how it's going to look like. All right, so we have a country, wherever that shape is. This is just for illustration, of course, so we haven't drawn anything, but it's kind of model that's empty model that doesn't have any agents inside. Now we want to have agents inside. To have agents inside, first thing that we have to do is to define an agent class. This is an agent class, and we call it citizen. We want to have citizens in a country. And inside the brackets, we write agent, which means this class that we're defining right now is an agent class. And it's not a model class, but an agent class. Now for this citizen class, we need two different attributes. First, citizen name, and second, citizen ID. It's up to us to define what attributes we want to have for specific class. Now we have two classes, the country class and the citizen class. But as you can see, they are two separate classes. So how can we make sure that the citizens that we will create here are going to be included in the country that we'll create? So we need to connect them somehow. Now, because we know that the agents, or in this case citizens, will be located inside the country, so we need to initialize them. So we need to initialize the citizens inside the country class. And initialization is technical word of creating, or starting something, or creating something. This is how we can create the citizens. So we want to create, we need the country name, of course, but we also want to create n citizens. And for each time that we want to create a citizen out of those n's, we need to call the class citizen, this one. So think about it as kind of when you arrive to here, to this line, you are going to call this class n times. First time you're going to call it, you create one instance of that class, and you give it a name and ID. You call it another time, and that's another agent, another instance of that class. You give it another name and another ID, and you keep doing this n times. Let's see how we can create a model that has agents. Now we will create, we only call the country class. Now we need several information to be provided. The first one is the country name. We provide Netherlands as a country name. We want to provide how many citizens we want to create inside that model, n. And for that, we specify 5 citizens. We only need 5 citizens. But because we are calling the class agent, the citizen class here, n times, each time we need to provide a citizen name and a citizen ID, because those are attributes that are needed. The actual commands, by the way, in Python will be different, but this is a simple way of writing those commands just for illustration. Now for each agent, we provide a random name and a random ID. So we provided all the information needed for the country class to create a country that has 5 citizens. Now we run that line, and then this is what happens. We create an empty country, and then every time we iterate over the citizen class, we create citizen. Citizen 1, citizen 2, every one of them has name and has an ID. Citizen 3, citizen 4, and citizen 5. So by just doing this, we created a model that has 5 citizens that of course are not doing anything. They're just static. Now what to do with the model? Now we have a model that has 5 citizens, but those citizens are not doing anything. But in every agent-based model, there are so many interactions that can happen. There are so many things that could actually be modeled. So let's look at it from the perspective of an agent. Every agent has 2 things. It has a state. For example, you can think about it as health condition, sick or healthy, that's state. And it has some rules, like if sick, take medicine, right? So it has rules that kicks in depending on a state, for example. So that's one agent, and that's internal, engine, let's say, state rules, and they interact with one another, and the agent can do an action on itself, okay? Any agent has a capability of doing action on itself. The agents interacting with everything that's outside of that agent, there are several things that can happen. An agent can do actions on the environment, and it can also take input from the environment. Think about the environment as kind of the actual life. So input from the environment could be something like raining or not raining. If it's raining, then probably the agent will do something. Maybe they'll bring umbrella with them. Right? If it's not raining, then they will not bring umbrella with them. But the agent can do actions on the environment. For example, planting a tree. If an agent is planting a tree, that action is done on the environment because the environment will have one more tree that's planted. An agent can do actions on other agents, like exchanging money, right? They can, for example, give them money or give them anything or do anything to them, right? That's an action that's done to other agents. And agents can take input from other agents. Maybe they can check on, their condition and states and change their state based on that, right? And so mainly agents can interact with itself, can interact with the environment, and can also interact with other agents in outside of their internal state. Now let's talk a little bit about the concept of inheritance. There are two things. When you talk about inheritance, I mean, from the name, inheritance means taking something from a father, right? Or from someone who you can inherit from. Now, the concept of inheritance in Python, there are two things, the superclass and a subclass. We have something called subclass, and I have few examples here. The first one is vehicle. Vehicle is a superclass in this case, and we have subclasses. The moment that you have subclass of a superclass, the superclass becomes a superclass. But if you don't have subclasses, then this is not superclass. And a vehicle can have several subclasses in this case. So a vehicle can have a car, can be a car, can be a motorcycle, can be bicycle. So all of these subclasses inherit from the vehicle some of the common aspects. For example, movement. The ability to move is a characteristic of the vehicle which is inherited to all of them. So it's smart actually to define a class that's called vehicle that has all the common things like the movement, the wheels, regardless of the number, because motorcycle has 2 and car has 4, but having a wheel in the first place, for example, is something that belongs to a vehicle, and material and other things. And when we define all those common things, we can inherit them to subclasses, so we don't have to define them again for the car and motorcycle and a bicycle. So this is called superclass, and these are called subclasses. And these subclasses have some difference, have some stuff in common, which are everything that's in vehicle, but they have some differences. For example, a motorcycle has 2 wheels, while a car has 4 wheels. A bicycle does not have an engine, unless it's an e-bike, of course, but a normal one does not have an engine. The motorcycle and the car, they have an engine. So these are some of the differences. Another example is this one. So if we have a human, animal, and zombie, and we want to model all of them, right? It's smart now to look at the common things, of these 3 classes, and then create a superclass that has those common things, in this case, a walker, because all of these classes have the capability of walking, so it's smart actually to define a class that's walker that has the walking functionality that will be inherited to all 3 subclasses in this case. A shape, circle, triangle, and square, they all shape, so they can inherit the characteristics that belong to any shape in this case. And also, last example here, we have the bird. It could be chicken, it could be eagle, it could be a penguin, but also other birds as well. There are differences between these 3. Eagle can fly, chicken cannot fly, but all of them are birds. So all of them maybe have 2 legs, maybe, and other common things. Now that we are done with our recap on the classes, let's start building our first model in Mesa. Setting up the model. So before we start the actual coding, I would like to jump till the very end and show you what we are going to build today. So let's run everything first, and let's see the result of this model. Now this is the model that we would like to build together today. What we have here is a grid that's 10 by 10, so 10 ticks on the X and 10 ticks on the Y. And on each intersection between the two numbers, this is one location. And these red circles are agents that could be red, which means an agent that has some wealth, some money. And gray could be gray. And if one of these red circles turn into gray, then it means an agent that does not have any money, that's broke. And this is the number of step, well, the step that we are at right now. So we start from step 0 and we're going to reach step 100 and see what happens. So the rules are in each step of the model, every agent will go to a different location that's close to it. To next location could be right, left, top, bottom, or also the diagonal are included. And when they go to another place, so to another cell or another intersection here, they're going to search if they have any agents around them. And if they find at least one agent around them, they're going to give them 1 unit of wealth. And everybody is going to do this. And we're going to see how the model is going to change if there are agents who will turn into broke because of this behavior. So let's see. I'm going to run the model and it's going to step from 0 to 100 to see. I will just slow it down a little bit. Next frame. Look at this agent number 4, for example, or look at this agent here. Look what happens when I step to the right. It moved to here, but there are no agents around. It's not going to give anybody wealth. It has wealth, but it's not going to give anybody wealth. So next step will not be broke. Movement, 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 movement. So now we have 4 agents who are broke, who do not have any wealth, and they're hoping that they get wealth from other agents who are close by. For example, this guy here now should get 1 unit of wealth from this guy here. So it's either that this will be broke and this will have 1 unit of wealth, or both of them will have wealth, depending on how much wealth this agent has. Now, obviously, so the previous one, so this guy here moved to this place and this guy here moved to this place. This became broke and this became wealthy. As you can see, this became wealthy and this became broke because they crossed diagonals here. Keep doing this all the way till the end, and we see after 100 the wealth distribution. So at the end, we have 6 agents with wealth, and we have 4 agents without any wealth. So this is the very simple model that we are going to create together today, step by step, introducing all the all the functions that you need to be aware of, and all the concept and the things that you need to keep in mind to be able to create this model or similar models. Now that we have seen the endpoint of the model that we're going to build together today, let's see how we can create our agent class. So from that class, if we create that class, agent class, we'll be able to initialize a lot of instances of agents from that class. There is some information here that you can read, of course, but I'm going to comment on the code that's provided to you here. Now, the first thing that you have to do is, of course, to import the Mesa library, so you can use, wherever inside that library. Of course, given that you have installed Mesa in the first place, but that's provided in the guideline that I provided in the description below. You can always check which Mesa version you're using. In my case, it's 3.0.3. But as I said before, this code will also work. So this model will also work with a newer version of Mesa, up to at least 3.2.0. However, it does not use all the capabilities of the newer version of Mesa. Now, to create an agent, you need to provide few lines. First, you need to provide a name to your agent. In this case, we're going to call it money agent, because our model is about agents moving and exchanging money. So it makes sense for us to call it money agent. And inside the bracket, we have to write mesa.agent, which means the agent class of Mesa. So that's a class that Mesa has inside that we are going to inherit from. Now, for those who are not very familiar with the concept of inheritance and still would like to build an agent-based model, this actually means that our agent class, the money agent that we are creating right now, is an agent class. It's not a model class, for example, it's an agent class. Okay, so this is the first step of inheriting from the agent, but there is a complementary step I'm going to talk about after a moment. Now, after you define first the class name, now you have to provide a special method called a constructor. So the constructor, which is really something related to Python in general, is something that's provided all the time whenever you're creating a class. So this constructor, it checks what is underneath it, and it will actually run it at the same moment when you initialize that class. So for example, later on, when we want to create an agent instance, we are going to call this class, and everything under this init function, the constructor, will be automatically run. And everything that's not under this init will not be automatically run unless we call it. In this case, because we want every agent to have wealth, we're going to include the wealth under the init. So that every agent will have 1 unit of wealth. Now, we define the init and we provide it with few things here. The first thing is self, so that the agent can refer to itself. And the second thing that we have to provide is model. So whatever inside those brackets are usually called parameters. Okay, everything inside those brackets is called parameters. And the model, this one, is actually because we need to provide it to the agent so that the agent knows which model it belongs to. Every agent at the moment of creation needs to know the model that it will belong to, that it will be associated to, and that's here, and that's why we need to provide a model. Now, as I said before, the inheritance will not be completed just by providing the name of the class that it's inheriting from. We need to provide a separate line as well, which is calling the constructor of the parent class. So we agreed that this is called parent class, and this is called parent or superclass, of course, and this is called subclass. Now, for the parent class, we need to initialize, we need to call its constructor. This is how we can refer to the constructor of the superclass or the father class by writing super dot, and then we write the same thing as here, super dot, init, and then we also need to pass the model. So the model that we pass to the agent at the moment of creation will be passed to the init, to the constructor of the agent we're creating, and then will be passed again to the constructor of the agent that we're gonna inherit from. Okay? Now, if you find this as kind of complicated, what you need to know is that those two lines are always there. So whenever you're creating an agent, you need to define to provide the constructor of that agent, and you need also to also call the constructor of the parent agent, which is in this case the agent class. And you need to have the model in both of them because an agent need to be associated to a model, and the superclass needs the model as one of the parameters. Now, when you do that, now you can define whatever attribute you want to have to your agent. In this case, we want to have only one attribute, which is a wealth. So we want every agent that we're creating to start with a wealth that's equal to 1. That's fixed. And now each agent will start with a wealth attribute of 1. Now, if we run this code, nothing would happen, of course, because we haven't done enough actually to see any kind of behavior yet. Now that we have seen how we can create an agent, let's see how we can create a model. So in a very similar way, we also have to define a new class. In this case, we want to call it money model because of course it's a model, but it's also about, exchanging money. So it makes sense to call it money model, but you can call it whatever you want. Now we inherit from a different superclass. In this case, it's model class. That's a model class that's defined already inside Mesa that we're going to inherit from. Or in simple terms, the money model that we are creating right now is a model class and not an agent class, for example. Now, because this is a class, we need to provide it with its constructor, def, init, and then it needs a self so that it can refer to itself. But it also needs something else, which is the number of agents. You will find this in every agent-based model, and every model needs to know how many agents is gonna be inside. We have the super to call the constructor of the father class or superclass this one, and this is how we do it, super init. But here, unlike the agent, because in the agent we pass the model, we need to pass the model. Here there is nothing to pass, but we still need to provide this super constructor here anyway to complete the inheritance from the model. Okay, and one of the attributes that we want for our model is the number of agents. So we define a variable called or attribute called the number of agents, and this is going to be equal to n, which is this one. Now, at the moment of creating an instance of the model, that we have to also pass the n, which is the number of agents that we want to create. Okay, and this will be associated with this attribute. So for that model, we will have a number of agents that's equal to n. Okay, so this is this is the only attribute that we need for our model. Now we need to create agents, and this is how we can create agents. It's still under the init function, under the constructor. It means when we create an instance of that class later on, then the agents will be created automatically, so without us having to create them again. Because as I said before, everything that's under the constructor will be initialized automatically at the moment of initializing the class that we're at. Okay, and this is how we can create agents. So we iterate over the number of agents. So for I in the range of self dot number of agents, so from I to the number of agent of that model. There's like a iteration of n times in this case. So every time we create an agent, this is how we do it. You can store it in a variable called a, and it's gonna be overwritten every time you iterate, of course, and it will be added automatically to the model. So a equal the money agent, which is the name of the agent class, this one here. So we're calling this, and by calling this, all of that will be initialized automatically for every agent. So every time we call this, we will have all these. So we'll have an agent that needs a model, and that will have a wealth equal to 1. So we need to pass the model, and the agent that will be created will have a wealth of 1. Now, money agent, we need to pass the model here. And this is how we do it. We just pass the self of that model. So this is a self, not of the agent, but of that model. So this one here. We pass it. So it means the agent that will be created, it knows which model it's going to be associated with, which is this one. Okay. And this is how we can create a model that has an agent inside that are still not doing anything. Now that we have created an agent and a model class, now let's see how we can add actions to the agents and how we can add step method that deals actually with the time, because we're going to create a dynamic model. So every step is going to, something is going to happen. So let's see how we can implement these two here. So again, we're going to build on what we had before. So we had the money agent and we had the init function here, and we had super init and we had the self dot wealth. So that's something we already had. Now, to allow agents to make a certain action, we need to add a method called step. Now, it could be called step, but it could be called something else. So it could be called give or take or just do step or whatever you want to call it. So this step is not fixed. You can just name it whatever you want. But later on, when you call this step, it needs to be the same name as you provide here. So this is how we can define the step. And then we provide it with a self, of course. And then under this step, we define the action that you want your agent to do if this function is called. In this case, we want every one of our agents to simply print its unique ID. So every agent, when triggered, it will say, "Hi, I am agent," and this is how we can retrieve the ID of that agent, which is already tracked by Mesa. So this is not something we define, but that's something we can also get. And that's mainly because we have inherited from the superclass agent. So now the agent knows that it has a unique ID, and that's it got from that superclass. So self.uniqueID, turn it into string and print it. All right. Now every agent will make an action, will do an action when it's triggered. Okay, so this is the only change that we've done to the agent. Let's see what kind of changes we need to introduce to the model so that we can have a complete, a model that allows for this kind of behavior, which is printing name and ID. Now this is a model class. We had this before, and we had this before, we had this before, and we had this before. We could also before create, the agents. And we have to define a step method for the model. This is how we do it. Define step, and we provide it with a self, which is the self of this model. And inside, this is how we can actually trigger the step method of the agent. This is how we do this. So this is a method provided by Mesa that allows us to do this. Self, so this model, dot agent shuffle do, agent dot shuffle do step. So maybe this step is actually this one. So if you change the name of this step, call it like do, then this has to be do as well. If you name it as give, this has to be give as well. Okay, and agent dot shuffle do, this what this will do is that it will trigger all agents in a random order to take a step. Okay, just by calling this later on, and we're gonna see how we can call this, how we can step our model, all agents will be iterated over in a random order because we have shuffle. Sometimes we don't have shuffle. If you write just do, then they will be triggered in the same order they were created. But when you have a shuffle do, this one, then the agents will be created, the agents will be triggered in random order. Okay, and now we're gonna see how this is done. Okay, now what we have is kind of complete model, but it's not running yet. How do we run a model? Now we have the money agent class and we have the money model class. We're creating agent inside the model and we have the step function. So we have all components, all ingredients to have a running model. But let's see how we can run a model. First, we need to, because these are classes, and I said before, a class is it's just a template. You cannot use it immediately. What you can do is that you can create an instance of that class. So here we want to create an instance of the model class, and that will be called one instance of that model class. And then inside, when we create that instance, we will also be creating a lot of instances of them from the agent class. So we only need to create an instance of the model class, and then the instances of the agent class will be created automatically. This is how we can create an instance of the model. We can call it whatever we want. Let's call it here an empty model. It means empty model in the sense that, well, this model is still not really doing a lot of stuff, just saying name, so there's not actual behavior happening. We call it empty model. You can call it whatever you want. This is how we can create an instance of the model class. So we call its name money model, this one, and we need to provide it with, let's see what we need to provide with. We need to provide it with the number of agents, in this case n, which is 10. So we pass the 10, it will know because it's only n that's needed. Then then it will actually map this number that we provided with this parameter that's needed. Okay, this line means we are creating a model instance, but still we're not running the models. Like we have a model that's not running, and this is how we can run the model. So every time we write empty model, so it's exactly this one, dot step, it means we are stepping the model by one step. Okay, and then we are of course seeing the result of the model. So let's see if we step the model by one step, what happens. So we are here. So we get all agents to tell, hi, I am agent, and then their unique ID. Okay? And as you can see, they are triggered in a random order, and that's mainly because we used shuffle do instead of just do. And now every time you run it, you get different results because every time it's triggered differently, the order of the agents, I mean. So every time you get different results, but that's all one step. So one single step, one time we call this. So we're calling this. This guy here will trigger all the agents. And we have 10, and that's why we have 10 lines here, but they are triggered in a random order. Okay. Run the above code one more time and see what happens. That's exactly the same code, and this is meant just to experiment with the randomness here. See? We get different result every time. Now let's try to change shuffle do into do, because this is another method that's provided by Mesa that allows us to trigger the agents in the same order they were created. So always agent number 1 will start first, and agent number 2 will start second. Let's run these classes. Let's update them by running them. We update them, and now let's create a model and run a step. See? Every time agent number 1 first, agent number 2 second, and agent number 10 last. Let's change this to shuffle do and go ahead. All right. Now each time, let's read this together. So each time you run this simulation, the agents are activated differently, and this does not really help with reproducibility. So imagine that you want to run this code tomorrow because you want to show it to your supervisor, and you want to show your supervisor the result that you get now and not different results. You cannot do this because it's giving you different result each time, right? But this does not help actually with reproducibility. To address this, we can use something called random seed. And there's a way actually on how to define it. And this random seed will ensure that the random number generation is the same each time you run the simulation. So each time you create a model and run the simulation, you get the same result at the same step. So if you run a simulation number 1, for example, at step number 1, you will get exactly the same result of another simulation that you run on another day at the same step, which is step number 1. So always step number 1 of any simulation will have exactly the same results. Similarly, simulation 1, but step number 2 will have the same result as simulation number 2 and step number 2. So always, regardless of the number of simulation, you always get the same result at the same step. Let's experiment a little bit with random seed for reproducibility. Now, to achieve this behavior of having the same result at every step, and this random seed is not really relevant only to Mesa and Agent-based model. It's something that's built in Python already, but it's very important to Mesa, and that's why I dedicate here part on explaining it, because there's a specific way on how you can define the seed. So let me show you how we can define it. So this is the model that we had before. We're not going to touch the agent. We're only going to change few things in the model. So this is the model that we had before. The only thing that we're going to change here is inside the, well, two things actually we have to change. First is inside the constructor of that model class. We're going to add seed, right? And then the value of the seed will be first none. It means it has a seed, but I do not set a value for it right now. I'm going to set it later on at the moment of creating an instance of that class. Of course, you can set the number of the seed, the number that you want. It doesn't matter which number. You can set as 10 or 100, whatever. But then it's going to be fixed for all the model that you create. So maybe you want to postpone this decision to later, and you set this to none in the beginning. So this gives you the ability to define a seed later on, but it does not specify the number right now. It just postpones it to later. So now we have the capability of using a seed, and we also need to provide it to pass this seed also to the super class here. And this is how we do it. Before we had that init, super init empty, but now we have seed equal that seed. So the same seed that's provided to this constructor will also be provided to the constructor of the superclass. Seed equal none, seed equal seed. That's what you have to know. And that's it. Now let's save those changes that we introduce by just running this cell. So we're gonna have an updated money model and the agent updated money model class. And the agent class will still be the same, as before. So we don't have to write it again here because we had it before. Now we have updated money model that allows for having a seed. Now let's create another model. I'm going to call it the same empty model. And by calling the money model here, we still need to provide it with a number of agents, in this case 10 agents. But now we need to give it a specific seed, right? We need to pass the number of seed that we want to use, in this case 1, 2, 3. If you don't pass the seed, it's going to take it as none, as if there is no seed at all. So the advice here is that you always have seed equal to none and only use it if you want to. If you don't want to, you can just remove it like that, and then it's like there is no seed. Now, what is this number? What should this number do? Whatever. It can be any number. As long as you're sticking to that number, everything is going to be fine. It could be 1, 2, 3, 1, 2, 3, whatever, any number that you like. So we choose here seed for reproducibility. Any seed will work, but you have to stick with it. Okay? We create a model and we run a step. And let's see what happens. Now, every time we run the cell, we get the same result, right? It's still random, but we're getting the same result. This is the first step. So this is one simulation. What I'm doing here is I'm creating a simulation. And these are the result of the first step of the simulation. This is another simulation now if I run it again. So it's simulation number 2. and step number 1. It means simulation 1, step 1 equals simulation 2, step 1. Notice that we get the same result every time we run the model with the same seed. So this is the result at the first step. Try to run another step and see that the result changed. Of course, simulation 1, step 1 equals simulation 2, step 1. But if we step the model further, then we get different result, of course, because the result will not be the same at each step. This is another step. See, the result of the second step are different from the result of the first step, although we use seed. But if we do another model, another simulation here, and we step the model one more step, then we get the same result. Now, if we want to step the model a third time, you get different result. So remember, 2, 9, 6. Let's try it again here. So new simulation by running this. So 2, 9, 6, right? But we need to step 2 times to get these values. 1, 2, 2, 9, 6. So by setting a seed, we ensure that the random processes in the model are repeatable. They are still random, but they are repeatable. You always get the same results at the same step, and that's very important to remember. Now challenge, try different ways of activating the agents, change shuffle to just do and see the impact. We've tried it before because the do will actually eliminate the randomness of the shuffle, then the seed will not do anything because anyway there is no randomness, so there's nothing that the seed can do. Now we have a complete model, but it's not doing anything that's interesting since every agent will is only telling what their unique ID is, right? To make the model a little bit more interesting, we need to add additional behavior, that the agent can do at each step. Let's do that. Now, this is a behavior that we want to implement. We want each agent to be able to give to give 1 unit of wealth to a random other agent if their wealth is greater than 0. So if they have money at all, they're going to give 1 unit of wealth to another agent. And we want to run the model for a few steps to see how the agent activation order is shuffled each time, right? Or actually to see the results. Let's see how we can do this. So this is what we already had before, the money agent class and the init and the self.wealth. We also had the step function before, but the only action that every agent was doing is actually to tell what their unique ID is. Now we want to change this and actually introduce a proper behavior, which is this one. Now, yeah, they're going to give money to to another random agent if they have money at all. So we need first to check if they have wealth. So self, which is this agent that we are at right now, dot wealth, so the wealth of that agent, if it's equal to 0, then return. It means return, go out of this function, don't do anything in this step, nothing will be done, and these 3 lines will not be executed. If it's not the case, which means if that agent has wealth, then these lines would be executed. First, we want to define another agent. We want to define another agent, and this is how we can do this. We call it something. In this case, we call it other agent equal, and this line chooses another agent at random. So let's see itself.random.choice, and this is a method provided by Mesa already, so we don't have to hard code it ourselves. We just use it because we know that it exists. And inside we have self.model.agent. So what this means is that I want to have all the agents that are in the model that this agent is associated with. So all agents of the model that this agent is associated with. And when you get these, choose one of them at random. Always like to read from right to left to understand what that command actually means. Okay. Um, and associated with a variable called other agent. All right, so now we have another agent that we've chosen randomly. Now we need to give that agent one unit of wealth because we have wealth. So we're going to give it one other agent dot wealth increase by one. This means increase by one. And then because we've given wealth, we need to lose one unit of wealth, self.wealth. So the wealth of the agent of this, the agent that we are at right now will be reduced by one. Okay, and this is the kind of behavior we want to implement to the agent. Now let's run the model. Here's how we can run the model. Now we're not gonna use seed here. So model, now we call it model. We used to call it empty model, but now since we have some behavior, let's call it something else. Model equal is an instance of the money model class, which we defined above. It's still there. And just to update the agent class, we have to run it. Now, the previous one is overwritten with this one. Now, this is the new behavior is now there. Okay, so to create a model is an instance of the money model, and we want 10 agents. All right. But now we want to run the model for 10 steps, not only one step, because here we've run it for one step. And every time we click, we run the cell, it means we are stepping the model. But now we want to step directly 10 times already. And for that, we create for loop for underscore. Sometimes you write for I in the range, but if you're not using I, it's better to write underscore. For underscore in the range of 10, so 10 times, step the model every time. So this means we're stepping the model, we run the model for 10 steps. Okay? All right. So we run the cell. Okay, now we have a model that is at step number 10. We do not see any result yet because we haven't extracted the result. That's what we're gonna see now. Now, because we want to use matplotlib and we are using Jupyter Notebook, it's important to provide this line, percentage matplotlib inline for Jupyter Notebook and the full, yeah, of course, so that we can see result of the matplotlib inside Jupyter Notebook. Okay. Now let's collect the wealth of each agent into kind of a list. So now at step number 10 of the simulation that we ran already, we want to have a list that includes the wealth of our 10 agents. So a list of 10 different numbers of wealth. This is how we can do it. We can use list comprehension to do that. First, we define a variable called, in this case, agent underscore wealth, and equal that list comprehension. And this actually means, again, reading from right to left. I want all the agents of the model, this model here, same name, okay? All the agents of this model, and then go over each agent of the agents. So every element of this collection here. So each agent of those agents get their wealth and store it in this list. Okay, so it's going to iterate over all agents, and every time it gets into an agent, it's gonna extract its wealth and store it into this list. Very neat way of extracting, number and storing it in a list in a straightforward manner. Again, it's called list comprehension. Let's draw this plot.histogram agent wealth. So we get this line. So if we run it, we get this. Okay, so we have 4 agents that have no wealth at all. We have 3 agents that have 1 unit of wealth, and we have 2 agents that have 2 units of wealth, and we have 1 agent that has 3 units of wealth. So this is what we get. But now, of course, if we run this model again here, we get different results. In this case, we have 6 agents who have no wealth. Of course, all the time we're talking about step number 10, right? Because this is what we're doing here. And we have 6 agents that have no wealth, 3 have 2 and 1 that have 4. And if you do the math, then you're gonna get 4 plus 3 plus 3. So the total number of wealth is 10, which is expected because we started with 1 wealth each, so summation will always be equal to 10. Okay, right? But every time that we're running this model, we're getting different results, of course, because we're not using seed, but we don't want to use seed here in this context. But we're not able to get like a specific behavior of the model because every time is different. So how can we, get some useful insight and information about how our model behaves? And this gets me into the model behavior. So to get a better idea of how model behaves, we can create multiple model runs and see the distribution that emerges from all of them. And we can do this with a nested for loop. This is mainly doing a Monte Carlo simulation where we run the model multiple times and we sort the results all together and see the behavior. Let's see how we can do this, and let's see the benefit that it can get us. First, we want to define a list where we're going to store everything that we're collecting. We are going to call it all wealth. So here we initialize an empty list to store wealth data. This is empty. It's up to us to define what the name of that is. Then we're going to loop over the model. We're going to run the model 100 times. Okay, for J, in the range of 100, create a model every time. So we're creating 100 model here. Model equal, from the money model, we want 10 agents. Every time, create a new instance of the model with 10 agents. And now for each of these 100 models, step the model 10 times by having this for loop for I in the range of 10 model.step. Okay, so at the end, we will have 100 models. Each of these models will be stepped 10 times, so we'll be at step number 10 and number 10 of each of those models. Now we also, inside this for loop, every time we are done with the model, we are stepping the model for 10 times, we're collecting also the data. For agent in model.agents, all wealth, which is this guy here, we're going to append the agent.wealth. Okay? So from all the agents of the model, and for each agent of those agents, get their wealth and append it to all wealth here. So the first time we are creating a model. So for the first model, we will have 10 agents with their wealth that we're collecting all of their wealth. So we're going to have 10 numbers here and the all wealth. And for the second model, we have new 10 entries. So all wealth will have 20. And the third one will have 30. So the number of wealth that we have here in this list at the end, when we're done with all 100 models, will be 100 times 10, which is 1,000 entry. And then we're going to plot the result again, plot histogram. Now we want to plot all wealth and we want to bins range. Of course, you can look this up because it's just a Python thing that defines how you want the bin to be and the maximum and everything. And this is the result we get. Now, this is the result that we get. So if we run it, let me run it because this is old one. So we get this. Okay, it means more than 100 or like 150 entries are agents that do not have wealth. 300 do have one wealth. Kind of 180 that have two wealth, etc., etc. As you can see, it's kind of starts to show some kind of distribution of a lot of agents do not have wealth, but then the amount of wealthy agents decrease with time. Let's run this again. See, do we have the same behavior here? It's different one, but it's same behavior. So every time we are running this cell, we're getting the same behavior. And that's the benefit of running a Monte Carlo simulation, of running many simulations of the same model to get some insight about the behavior of that model. Let me show you again what we had before. See, it's very different because it's single simulation, right? And when we have many altogether, combine them, we get the same behavior, which is fascinating actually. So you can actually draw a conclusion out of this. You can confidently say that, well, for my model, always at step number 9, I'm having a lot of broke agents and really few wealthy agents. But we cannot do that. We cannot draw this conclusion from that. So up to this point, we had some behavior of agents exchanging money, but those agents are not really moving on any kind of space. They're just finding other agents randomly and exchanging money with them. Now, what we want to do, we want to add a little bit more complexity to our model, and we want the agents to move before actually exchanging any money. And to be able to move, to add this spatial dimension, we have to use Mesa spaces, which is a functionality added by inside Mesa that we can actually use immediately. And let's see how we can add a space. You're talking about like a word, how we can add a word, how we can add like place or space or a grid, whatever you want to call it, where agents can actually move around on. Now, for this version of Mesa that we're using in this tutorial, you have two main types of grids. The first one is called single grid and the other one called multi-grid. Now, single grid enforces at most one agent per cell, so you cannot have more than one agent as specific cell, okay? And for the multi-grid, it allows for multiple agents to be on the same cell. But here in this model, we want agents to be able to share a cell, and that's why we're going to use multi-grid. Let's see what we have. Now we again start from something that we had before. So we had the class money model, we had the init, we had the super, and we had the number of agents, but we didn't have grid yet. And this is how we can define a grid. Self.grid, okay, you can call this whatever you want here because it's grid, we're going to call it grid. And we're going to use the multi-grid of Mesa. So this is space module that's inside Mesa, and this is the multi-grid, object that's inside the space, and it needs three things: the width, the height, and the torus. And torus could be true and false, and torus means making the grid wraps around. So, for example, if this is your grid, if you have agents here and they go to the right, they will appear on the other side. So it's like wrapping it around so that it's kind of continuous. Here we want to wrap it around, and so we set torus to be true. Again, multi-grid allows multiple agents in a cell. Torus true makes the grid wraps around. We again create agents after we added the grid, we create a agent as we did before, but now because we have grid, it's not enough to only create agents and add them to the model, but also we need to place them on the grid, and this is how we can place them on the grid. First, we need to define a location on the grid, so x and y. X is self random range in the parentheses self.grid.width. It means the width, take the width of the grid of this model and pick one point of that width because it's discrete. For example, if it's from 1 to 10, then pick any number, any natural number from 1 to 10 randomly, okay? And assign it to x. And we do the same thing with y. Self.grid.height, random range, random, and we assign it to y. So x and y will be two numbers from 0 to the width, or the height in the case of y. And then this is how we can place agents on a grid. Self is for the model, of course. Dot grid, so the grid of the model, place an agent on the grid of the model. This is how you can understand, always start from the right, and place that agent with that coordinates. So that coordinates, that agent, consider that agent and consider and place it on this coordinates on the grid that we defined, of course. So place the agent at coordinates x and y. This is how you can place agents. Okay, now we defined space and we placed agents on the space, but let's see now how we can move agents, how we can allow agents to move. So we need to add a new function to the agent that allows them to move, and that's a move function. So everything that we defined before will hold true, of course. So I'm not gonna repeat them, but this is the one additional function that we need, and we call it move. And at some point, at the end, I'm gonna put everything together so you can see all the agent class, or all the methods, all the function inside the agent class all together. So define move function. This is how we want the agent to move. So we want the agent um, to move to any of the 8 directions that's around it, because every cell on a grid, it has 8 different cells that are in the neighborhood. First, we want to get the neighborhood of that cell. So get the neighboring cell, possible steps. These are the steps that an agent can do given its current location. Possible steps equal, we are going to use the get neighborhood method that's inside Mesa. So the get neighborhood method of the grid of the model that this agent is associated with, and that get neighborhood, it needs these parameters. So the position of the agent, the more, whether it's true or false, more. If it's true, it allows, it includes diagonals. If it's false, it does not include the diagonals. So if it's false, it's only 4 cells that are in the neighborhood, up, bottom, right, and left. And if it's 8, if it's true, then it's also the diagonals as well. So it's 8. And whether you want to include the center or not, if you want to move to your same location. In this case, we don't want to move in the same location, so we exclude the cell where the agent is currently located. Okay, after we define the possible steps, we need to choose one of these possible steps. So we need to choose a new position, and this is how we can choose a new position. From the possible steps that we defined here, choose one step randomly and assign it to a new position. So now we have a new position that's a random position from all the possible steps that we defined before. Okay, and now we want to assign this new position to that agent. This is how we can do this. We're going to use the method move agent. This is how we move the agent, which is a method of the grid. So the method move agent of the grid of the model that this agent is associated with, and we have to provide that agent. So which agent we're talking about, in this case self, okay, and the new position, and it will move that agent to that new position. Okay, now our agent can move, but we also want to give money to one of the other agents that are present at the same cell. So before we used to give money randomly, but now we want to change that behavior so that every agent will give money to only 2 agents who are on the same cell. So we need to check who else is on the same cell. Okay, so everything that we've defined before, including the move, is there. It's hidden. So we're just gonna write a new function that's give money. So we define a new function, we call it give money. And all right, so because we want to check other agents who are on the same cells, so we define new variable called called cellmates. And this is the command that we use in this case. So get cell list contents. So this a method here or function here allows us to extract all the contents that are in the cell. In this case, other agents. So this is a method of the grid. So get cell list contents of that grid, of that model, etc. And it needs only one thing, which is a position of the agent. So if we give it the position of that agent, it's gonna tell us who else is placed on this very cell. And we assign all these to the variable that's called cellmates. Now, if the length of the cellmate is greater than 1, so 2, 3, etc., it means there is more than one agent in the cell. So if length of this cellmate's object is greater than 1, it means we have more than one agent in the cell. Okay, so it's not only the agent that's on the cell, but there are also other cellmates actually on the same cell. Because if it's equal to 1, it means it's only that agent that's placed, so there's no cellmates there. So we check that first. If length of a cellmate is greater than 1, then we need to choose another agent. And this is how we do this, using the random choice. From cellmate, we're going to choose one from a cellmate, and we're going to assign it to a variable called other. Now, if that other is different from self, because it could be ourself, it could be the same agent. So we check if that other is different than self, then we give them one unit of wealth, and we extract one unit of wealth from the agent. Other.wealth increased by 1, and self.wealth reduced by 1. Okay? And with those two methods, the agent step method becomes that. Now we need to also change the step method that we had before. So first, we want every agent first to move self.move by calling the move function that we defined here. So they are going to move according to this behavior here. And then when they move, after they move, we're gonna check their wealth. If they have any wealth, we're going to call the give money function that you find here. We're gonna implement this, which means they're gonna check if they have any cellmates, and they will give them 1 unit of wealth and deduct 1 wealth from their own. And this is our new step function of the agent. Now let's put everything together. This is what we have right now: money agent, the init, initial wealth. Now we have the move function, which is the one we've just written, and we have the give function, which is exactly what we had before, and we have the step function. Now for the model, it's exactly the same, because the only thing that we're doing here, that we used to do here, is to shuffle do step, which is the same, but whatever happening inside the step is now different, so we do not change the money model. Now let's create a model with 50 agents, and now we need to, because we have a grid, we need to define the width and the length of that grid, in this case 10 by 10, and we want to run our model for 20 steps. So new model equal money model 50 agents, width equal, so in the same order. So first one is for the n, second for the width, and third for the height. This means we are initializing the model with 50 agents in a 10 times 10 grid. And we want to run the model for 20 steps. So for I in the range of 20, model.step, it's going to iterate over I from 1 to 20 or from 0 to 19, because that's Python. And every time we're going to step the model for one step, it means 20 steps in total. Okay, let's make sure we have run this just to update everything. And then we run this model and we step the model for 20 steps. Okay, and now let's do some visualization. Here we are using a Seaborn library, because it's just better way of visualizing. And here what we have is it is a heat map. So we are using the heat map method of Seaborn. Of course, feel free to to look this up. But this is really a Seaborn thing, and not Mesa thing, but we're gonna use just for visualization. And this is the result that we get. So we have a grid with a heat map, and then with a number of agents at every cell. So from 0 to 9, which is 10 ticks, and from 0 to 9, which is 10 ticks here. And at every intersection is a location, and we have the number of agent that is located. So if you count all these number, you get the total number of agent. It should be 20. 3, 4, 5, 6, 7, 8, 9, 10, 12, 11, 13, 15. It's more than that because we have 50 agents. Sorry, I thought 20. So if you sum everything up, it should be 50 agents. Yeah, 50. So let's see now how we can collect the data. So up to this point, we've been only able to check the result at the last time step of the model. But what if we want to, collect all the data that we have at every single step of the model, and we want to collect many things at the same time? What can we do? So there is a module, or there is a way in Mesa that's called data collector that allows us to collect, data at every time step in a very simple way. So let's see how the data collector works. First, let's define, a function that computes something so that we can collect it, so that we can compute it in the model, in the simulation later on, and then collect the result of that function. So we're gonna create a function called compute Gini, which is Gini is a coefficient. If you're not aware of, if it's a coefficient that is ranged between 0 and 1, where 0 represent perfect equality of income in this case, and 1 represent perfect inequality. So if our model has a Gini coefficient of 0, then all of our agents in that model has the same amount of wealth. And if it's equal to 1, then one individual has all the income or all the wealth in the model, and everybody else have no wealth at all. So this is how the Gini coefficient or Gini function looks like. Of course, you can go in details and see what's going on, but mainly it's gonna return the Gini coefficient at the end. So whenever we call this function and we give it a specific model, so it's gonna do this computation and it will return Gini coefficient to us that we could collect. So now we're interested in collection, in data collection and collecting of data, not actually in what this Gini coefficient does. So now in order to introduce the data collector, now this is the same agent that we had before, so we don't have any we do not introduce any changes to it, because the data collector is something that we introduce that belongs to the model that we introduce in the model. So this is a model class that we had before. So we had the agent, we had the grid, and this is how we created the agent before. So nothing new here so far. This is how we introduce the data collector. Self.data collector. So this is the name that we give. It could be anything that you want. Equal Mesa.data collector. And this is the method that Mesa uses, that Mesa has already built in, that we can use immediately. So data collector, it's a dictionary that it's a tuple of two things. The first one is model reporters. So in the model reporters, we have all the things that belong to the model that we want to collect. And in the agent reporters, we have everything that belongs to the agent at the agent level and that we want to collect. So the data collector includes a tuple of two items. Now, every one of these two items is a dictionary that has a key and a value. For the model reporters, we want to collect a Gini coefficient that we have written a function for. So we call it whatever we want. In this case, we call it Gini. So our key is called Gini, and then the value is called compute Gini, which is a function. Now, um, it is going to call this function and it's going to do this computation and it's going to get the output of this function, and it will assign it to this key, which is Genie, and that's done at every time step, of course. And for the agent reporters, we want to collect the wealth. So we call the key is wealth, and also the attribute that we want to collect is also the wealth, right? But whenever you're collecting an attribute, you put it in the code, like quotation marks, as we're doing here. Whenever you're collecting a function, you just call the function as is, so you do not put it in a code. And if you don't put the attribute in a quotation, it's going to return an error. Okay, now we have data collector already set up. Now we want to collect data at step 0 before we run any simulation. So that's the initial state. So we collect the data at step 0, and this is how we do it. Self.dataCollector, which is this guy that we defined here. And we ask it to collect at this time step that we are at right now, which is because it's still in the init. So we haven't done anything yet. So we collect step number 0. All right. And now inside the step function of the model, we need also to collect data at every time step. Now we have this, you know, this activation command, right? So at every step, we're going to activate all the agents. And when we activate them and do their action, then we are going to collect these two guys here every time step. So if we run this 100 times, this will be triggered 100 times. So we have the data of every single step for whatever we have here. And this is how we can collect data. So let's run the code and see. So we create a model, which is an instance of the money model, 10 agents, width equal to 10 and height equal to 10. And we want to run the model this time 100 times, 100 steps. And of course, we should expect that we're going to collect data of 100 steps plus 1. So now we have run the model for 100 times and we have collected all the data that we want, but they're just not seen to us unless we extract them. So let's extract some of the data that we are interested in seeing. For example, let's extract the data related to Genie. So we define a variable called Genie, which is equal. This is how we extract data. Now we want to get the whole data frame, okay, the whole table, let's call it. That includes all the Gini coefficients at every time step. This is how we can do it because Genie is at the model level. So this is how we can extract the model level data, get model variables vars data frame method. And this is a method of the data collector of the model that we have. So this guy here. Okay. And we assign it to Genie. Usually when you write that command here, you get all the data that you collected. But because we are only collecting Genie coefficient here, then all the data that we have at the model level will be chaining. And that's why we call it Genie immediately. Okay. So this is how we can collect. Okay. And this is how we can show. So we just write it as it is. So if we don't have that guy here, then we run it. We should run the model. We should run this one. And then if we run this, okay, it's stored in Genie, but it's not visible unless you retrieve it by writing the variable name again. And this is what you get. So a long table with time steps here from 0 to 99 because we have 100 steps. And for every step, you have the Gini coefficient. We start from 0 because we start from every agent having one unit of wealth, so that's equal a perfect equality. And that's what we said before about Gini. When it's zero, then it's equal equality. Then Gini will increase because there will be no perfect equality anymore because of the exchange in money. Okay. All right. Let's plot the data just to see everything because checking a table is not really. It's difficult to draw any insight out of it. So let's plot. The results of the Gini, and from it we get this curve, so we can see kind of behavior of Gini coefficient is increasing around something between 0.5 and 0.6, and it's then fluctuating. Now let's retrieve the agent level data. So we still use data collector dot, but now instead of get model, we write get agent variables data frame. And because the wealth is the only thing that we have collected, see here, we get all the data frame and we call it wealth. Agent wealth equal model.data collector dot get agents variables data frame. We retrieve agent wealth, and then we show that we display the last few entry here. Okay. If you don't have that, you have everything. But if you are interested only in the last entry, write tail. If you're interested in the first entries, you write hat. Okay. All right, everybody kind of starting from from one, but then at the end, tail, it's changing. This is the head. And this actually concludes the part about collecting data. So there's so much more that you can do with it. Now, let's see how we can visualize the data. Now, Mesa has a built-in method for visualizing data, but it's still kind of experimental. Sometimes it works, sometimes it doesn't really work. So they're still really working on and trying to improve it. We're expecting that this visualization module to get better really soon. So it's really at a level where we can really use it and rely on it. Currently, it's not the case. So there's that code that uses the visualization module in Mesa, but there's no guarantee that it works. So, but for the sake of this tutorial, I have written a script that allows us to see what's going on, and that's exactly what I show you what I showed you in the beginning of this tutorial today. And this script relies a lot on Matplotlib, on IPython. You don't really need to understand what's going on inside, um, but the main idea here is that visualization of the simulation is very important because it really allows you to see some of the dynamics that's usually difficult to see if you're just looking at data or at some plots of the data. It's always nice whenever you have the opportunity actually to build this kind of visualization. Do that because it will always give you some additional insight. And that's why I showed you before. We can see in every step the movement that's done. And here it really helps you to verify the model because maybe you see some agent are teleporting, going from one cell to very far cell, but that's not the behavior that you coded in the first place because you coded that every agent moves one step at a time, right? One cell at a time. But if this is not happening here, then there's an error. Yeah, it's very difficult to see if you don't have this kind of visualization. And so on. Now we have a complete model, but what if what if you want to run many simulations? You want to try different combinations. you are doing some experimentation for like some purpose, and you want to try different things at a time. How can you do it? Like, what if you want to try the effect of increasing the number of agents on your model? So what you would normally do is that you would run a simulation with 10 agents, and then you would run another simulation with 11 agents and with 12 and with 14. And then every time you collect the data and you find a way to put things together to compare them to draw some conclusion. Now we have something in a Mesa called batch runner that allows us to do these kind of, you know, combinations of or trying different, different values of the same variables, and creating different simulations, considering different combination of these values. There's a way to do that, and that's the batch runner. And this is what you should do in order to use the batch runner. Of course, whatever we had before, the model and the agents are the same. So as long as you had these two here, so after you have the money agent and money model, you can proceed and immediately implement a batch runner. And this is how you can do this. First, you want to define a variable called whatever you want to call it. In this case, we call it parameters. And it has the three things that we want to change. Well, these are the parameters that are required by our model. There's n, width, and height. So number of agent widths and height of the grid, right? Um, Now, if there is one of these, if one of these variables is a variable that you want to change, you provide different values for it. So what we're interested in this experimentation here that we're doing right now is to see the effect of changing agents. So we want to allow the agent numbers to vary from 10 to 50 and increments by 10. It means 10, 20, 30, 40, and 50. So we use it in numpy np.arrange. Of course, we should have already imported the numpy before. np.arrange from 10 to 51 every 10. It means 10, 20, 30, 40, and 50. So those are five different values for the number of agents. And then width 10, height 10. So it's only one value for each of these two parameters here, width and height. So how many simulations that we are going to do out of that? There are five different simulations. The first one is when you have 10 agents, width 10 and height 10. The second one, 20, 10, 10, 30, 10, 10, 40, 10, 10, and 50, 10, 10. So five different simulations. Now, you can also add additional value to the widths, for example, 10 and 20. And then the total number of simulation will then be 10 simulations, because this is the number of combination that you can get out of those. But for now, we're only gonna change the number of agents. Okay, so we define the parameters that we have, and those, especially those that want to vary. And now this is how we can execute the batch run. So we define a new variable. You call it whatever you want. In this case, we call it param run equal mesa.batch run. And this is a function that's defined by inside Mesa already. It needs the following parameters. So it needs the name of the model, which is, we call it money model. It needs the parameters, which are the parameters that we defined right now here. So all the parameters that the model require, but now with varying values. We need the number of iterations, so number of times each parameter combination is run. If you set this to 1, so the number of iteration or simulation will be 5. But if you set to 2, that every combination will run twice. So if this is 2, so you're gonna run 2 times the combination when you have 10 agents, and 2 times the combination when you have 20 agents. This is kind of getting more reliable results at the end. So or when I do Monte Carlo simulation, for example, of having multiple iteration for each combination, so the result will be trusted more. And now steps, maximum number of steps 30. That's the maximum number of steps the model runs for each iteration. Number of processes, if you're using parallel computing, then this is relevant. If not, just set this to 1, especially if your model is not complex. And data collection period, here you can identify at which step the data is collected. So you don't have to collect every time step. But in this case, we want to collect at every time step. We set it to 1, so each time step. And if you want to see the progress bar, this is the progress bar. Now, if we run this, and because that's it for the batch runner, then we can run the cell and then we can execute all the simulations. All simulation runs. Let's see, it's printing everything. Let's go again to it and not print everything for now. Okay. Let's restart the kernel because it seems to be like a little issue here. And let's run everything again and see what happens. Okay, so yeah, loading widget. Normally, there seems to be a little issue now with my current session here. Maybe I should refresh or something. But normally you see like loading bar, and that loading bar like gets filled as the simulation can getting towards the end. But it's still being executed. Now, if we want to see the result, we can run this parameter run, so we can check this, but we will get the long list. As we've seen before, we will get a long list of all the result in a really messy way. So let's do it again and see. This is what we get. It's very long list of all kind of results with run ID, with iteration, with steps, with everything all together. But this is not really a nice way of presenting a result. It seemed like a complex structure of lists containing dictionaries. Luckily, we can turn this into well-organized pandas data frame using a simple command. Okay, if you're not familiar with pandas, um, um, Mesa relies a lot on pandas for the data organization, and so pandas is very important to know the basics at least of pandas. Um, we want to store the result. It's something called batch 1D results because we're only changing one variable. If you're changing two variables, maybe we put 2Ds, but it's really up to us to name this data frame whatever we want. PD the dot data data frame. So this is a method that's inside pandas. If you in the previous cell we have already called, yeah, we have imported pandas, and that's why we can use PD now right now. Let's clear the output cell. Yeah, so now it's better. Just let's move this so that we don't get it again. Yes, so batch 1D results equal PD.data frame, that's a method of pandas, and then turn this parameter run, so whatever we got before this messy structure, into data frame, and show me the last 50, so the tail of that, and see how neat this is. So this is what we get. This is the last 50 rows of that big. So, and what we have here for every one of these rows is the run ID, because we said we have 5 different simulation runs, and it's starting from 0. See the head. It's starting from 0. So we have the run ID, we have the number of iteration, in this case only one iteration, which is iteration ID 0. We have the step, We have number of agents because in the first we have 10 agents, but later on we have 20 and then 30, 40, and 50 with height, Gini coefficient, agent ID, and wealth. So we're collecting everything together. Okay, so all the data are in one place. Okay, let's see the last ones. Here we have 4,650 rows because we're starting at 0, of course. So see here a number of, so this is 50, this is number of agents for that simulation is 50. But why do we have so many rows? Because for every single simulation run, we have 10 agents, I guess. We have a lot of agents, sorry. So we have 10 agents, and then we are also extracting the wealth of every agent of those 10 agents. But then for the simulation that has 20 agents, we're extracting the wealth of every agent of those 20 agents, and then for the 30, for 40. And that's why it gets really, really high. Okay? Now, if you do the math on how many rows you should get, it should be exactly this number. Okay, and this is how we can extract, but now let's visualize this data because this is very complex. I mean, you cannot get any insight out of it just by looking at it. So we need some kind of, plots to help us do that. Here we again use Seaborg. So what we want to plot is the following. So we have the number of steps. So we have 30 steps here, and we want the Gini coefficient. And we want to plot for each simulation. For each simulation, because we changed the number of agents from 10 to 50, so we want to draw all of them. So this plot here is related to simulation when we had 10 agents. This is 20s, this is 30, 40, and 50. Mainly, we just want to see the effect of increasing the number of agents exchanging money on the Gini coefficient. And we can confidently say that the increased number of agents will lead to more inequality, because the higher the Gini coefficient is, the more inequality we have. So the more population, high number of population we have in our world that are doing transaction, this leads to more wealth inequality. And now accessing pandas. Pandas is very important. So this was just one example to for the students who are gonna have access to this notebook to actually experiment with these pandas and trying to manipulate data in different ways. Because panda is very important to Mesa, and you really need to know pandas so that you can extract whatever number you want from this data frame, or number of rows or number of columns of combination of whatever you want. There's all kind of way that allows you to do that in pandas. So there are a lot of documentation out there for pandas. You can use this data frame that I present here to try different things. For example, what if you want to get the areas of all the cities of Canada? What if you want to get the population of one city of USA and one city of Canada? What if? There are a lot of what ifs that you can do to learn how you can extract data from a data frame. Now, to wrap up, so these were the learning objectives that we presented today in the beginning of this tutorial. So what we've done in this tutorial is that we discussed important concepts of Python, including, but not limited to, classes and inheritance. We have practiced a wide range of Python commands, and we built a minimal agent-based model, which is kind of simple economy model using the Mesa library.